R. Let me use R. And what do we have here? Some holes, right? It's like a golf course. If you like this golf course there. What's the point of this having this hole? Do you know? Because our vector field is not defined there, right? If it is defined there, actually there's no point of doing that, although it is still true, right? So, and then we have oriented boundary R, right? So outermost one is bounded like this, but inner one is a clockwise. The reason is that the region has to be on your left if it is, that's the principle. But if you look at this inside region, which is not the region R, this is not positively oriented, right? This is positively oriented to R, but not positively oriented for the inner region there. Okay. But if you have that situation, what is the theorem? Green's theorem says, if you integrate over this boundary that has three curves, three disconnected curve, right? Outermost curve to inner curve. So if you do that three integrals and add them all up, that's what that means, right? So the vector field. So to do that, do we require the curl being 0? Is that part of the condition? Yes or no? No. Green's theorem 2 does not require curl being 0. If curl is being 0, then it has wonderful consequences. But Green's theorem 2 itself doesn't require curl being 0. Curl appears here. If it is non-zero, you get non-zero right there, just like that area problem we did and went over in. If this is 0, then it has interesting consequences. But if it is non-zero, and it is like that. Okay? Curl doesn't have to be 0. To Green's theorem 2, does the region R have to be simply connected? Yes or no? Does it have to be simply connected for Green's theorem 2? No. No curl 0, no simply connected is necessary. Pretty general statement, right? So that's the Green's theorem. But for the line integral, what it means, consequence for the line integrals, right? What that means is that the outer curve C of this one, I used prime notation, but let me just use C1 and I'm going to write it down. Inside, clockwise rotated, I'm going to call that C1 and C2. Those are inside two curves. Okay? Not C1 prime, that's just simply C1. Then integrating outside is the same as integrating inside separately like this. And all the integrand is the same, so I'm not repeating that. That's an important consequence. So rather than going around like this, you can go around inside clockwise 2 times. Okay? Or if you have only one hole in there, you can just go around 1 time. And that's the same thing. So think about that today's quiz problem. If you have an ellipse there, right? And instead of going around ellipse, you can go around just a simple curve right there, right? So using the Green's theorem, you had this thing in the test problem, but rather than going around this ellipse, you can just go around that same old circle. And they're going to be the same, right? So integral is a lot easier. You don't have to go through some tricky Calc 2 technique to finish off that calc. This is going to be the same, whatever it is. That's the consequence of Green's theorem that we went over. Make sense? Makes more sense, maybe, since you've done examples in the homework and you thought about for 10 minutes that what is this about, so it probably makes more sense. All right. So today, and this is a consequence, and this manipulation that kind of makes sense. Today we're going to think about why is it so. There's a kind of explanation of, it says explanation from how to go from Green's theorem 1 to Green's theorem 2. Again, this region can be really complicated, so the difficulty of doing this mathematically rigorously, maybe it's comparable to the difficulty of proving Jordan curve theorem, but here I'm just going to use a very simple example and gives you an idea about that. So here is usually the book doesn't use this rectangular example, But I realize this rectangular is this fabulous example to introduce this one. So once you understood this rectangular example, you might understand all the other pictures you have in the book. It's easier to understand. So I'm just putting this random grid here. You can kind of even subdivide it like this. Doesn't matter. You can make it any way you want. Okay? And I realize that there is a problem spot right there. So I'm going to kind of indicate there is this vector field is not defined in that 2 points. Everywhere else is good. So I decided to shade it like this. Maybe I'm going to shade it around that problem spot. We call singularity even for that. Everywhere else is shaded. So simply connected or not, this region R. Simply connected? Not simply connected because of the hole in there, right? If the region has inside as a hole, just like a golf course, it's not simply connected. Everything inside must be filled in. So not simply connected. So that's an example of this thing. Now if I chop this one like this, individual thing, I'm going to label it R1. So I'm not really going to count this one, but at the end you end up at, let's say, Rn in general case, right? The number of rectangular boxes in there. So R is not simply connected region, correct? But individual RK is simply connected regions. Is that right? These rectangular box, each individual box has no holes in all. Correct? All right. So we have, we're looking at this following statement. Integrating a double integral of curl of f of dA. That's a part of the conclusion of the Green's theorem too, correct? And this is going to be equal to sum of little regions, right? What are the sum of the little regions? Okay, going from 1 through n. Can I divide it up to individual regions like this? Is that okay? So double integral over these n rectangular patches together is going to be, of course, first one over, second one over. It's going to be the same volume. Think about surface that's hovering over this guy, and this is representing the volume of that. Volume over that, volume over that, that will be the same. Okay? But individually, this one has Green's theorem 1. Why is that? Simply connected region. Green's theorem 1 is about a region that is simply connected, right? So I can apply simply connected region GT1 to those individual terms. So who wants to go for that? Okay, going from 1. If I apply Green's theorem to that double integral, because the region is simply connected, what do you get? It's a line integral, right? Line integral is the boundary, right? What is the boundary? RK. And this boundary symbol. And it means it's positively oriented, right? Okay. And then this one becomes what? Just FDR. That's the line integral. Individually, it's like this. Now, what you have to look at is the meaning. How does this integral fit together? So this is nice. This is the part that is magic kicks in. So this is arbitrary region RK. And I'm going to make it a little bit bigger. So it's arbitrary region RK, one of them. And this is positively oriented, right? That's what that means. Positively oriented, how does that go around? Clockwise or counterclockwise for RK here? Counterclockwise. So it's going like that, and it's going like that, and going like that, and going like that. Make sense? Now, next thing we're going to do is that you look at each side over here. Is this a boundary of R? You ask that question. What's R? R is this entire thing, right? So let's look at this guy right here. So maybe I should have divided further into it. This thing I'm doing makes more sense. Would that be all right? I fixed that a little bit. So everything must be rectangular and fit perfectly together, not oddly like that. If it's not, you can always divide it by further dividing and make it perfect and grid in there. So, for example, if you look at that side right there, if you're looking at this one as an RK, right there in the star, this one is a part of boundary of R. Is that right? Boundary of R is this outer boundary, and this was also the boundary, this inner boundary, right? So this can be a boundary of R, right? And you ask the same question. Is that the boundary of R? Is this the boundary of R? Is this the boundary of R? Right? Well, if that's so, you just don't touch it. Maybe that's the answer is no. To that one is no. That means that whatever the adjacent rectangle must be there if it's not the boundary, right? Okay. So there is one more rectangle is right next to it there. You agree? And how is this one oriented? Yeah, clockwise. So let me go ahead and put that. This is counterclockwise. Isn't that going like this way, right? Going that way. So I'm going to call that from here to there the gamma. Gamma, that boundary, which is not part of the boundary of original R, must be the boundary of one region. It must be boundary of another region, right? And there's no more region that is having that part as a boundary. Correct? So whatever this boundary is, you will see in this line integral, each of the line integral has 4 pieces in there, but that piece right there will appear one of these sum and appear in opposite direction. You see these two things are oppositely oriented, the line integral, and that's going to appear in opposite orientation in there, see, 0. Does that make sense? Let me summarize it here. This line will appear 2 times in this calculation right there. For one region and another region, and for both situations, they're opposite directions. Therefore, they will perfectly cancel. Line integral. Not double integral. Line integral will cancel perfectly, and that's what this is about. So you go around each of the boxes, whatever that belongs to, not belonging to the boundary of the original, not simply connected, multiply connected region, they're going to disappear, right? So therefore, what's going to remain in here? Everything that is a boundary of the original region. Those things will cancel out. Those things will cancel out always, right? Because there's always 2 regions touching in opposite orientation. So we're going to have some selection. I'm going to call that, I love this notation, some selection of this indices in there. And it's not even correct. It is kind of difficult to write at this. I have to introduce another load of notation. But some sort of weird summation in here. You have to break apart this in the region RK in there. Some pieces of this sides. Does this notation make sense? You remove everything that doesn't belong to the original part of R, right? Because they all cancel. And what you're left with, and if you put them all together, and this is always, if this part's yes, then it only belongs to one region, is always on the left because we always parameterize it positively, right? So these pieces is a perfect consistent orientation for the original one as well. Therefore, you can kind of in your mind, you agree that that must be what's left is the correctly oriented boundary of this thing. So you started from there, you end up at there. And what's left is the correct orientation of the outer boundary and inner boundary and things like that. That was a green stem too. And it has important consequences to us. All right? So that's why. But the reasons are not like this. And if you wonder and how you do other things, maybe I'm going to show you this wobbly example there and there like this. So you think you can divide it up into, what's the idea here? Is the idea is that dividing this one into simply connected regions, right? Simply connected regions so that you can apply Green's theorem to the individual part. So let me challenge you. I actually never thought about this. What is the simplest way to create a simply connected region? Right now, this is not simply connected region, right? If I divide it up like this, vertically, do you think left side and right side is simply connected? No, right? So somebody makes a suggestion. I'm going to draw from here to there and there to there, so that after that, each division seems like a simply connected region. So after the discussion, we discovered this line segment will create simply connected regions together. So see if that same argument applies. This doesn't belong to actual boundary of the original one, right? This is something we created. So it's going to cancel and cancel into the same thing. And you can go through this argument by yourself and looking at, okay, if I look at R2, for example, R2 looks like this. Agree? And that part of the boundary belongs to the original boundary, and these guys not. So it's going to cancel out, things like that, right? So that was a little demonstration with other things. And in the book, they have a bunch of other things that also go through that example. But the key thing is that noticing that these and these along this boundary, they have two sides next to it, and that's a better argument than looking at each of the examples. Finally,